Lecture 2.12, Train in a Tunnel. So this example will be dedicated to a single example. A train of length L0 has a velocity v as it goes through a tunnel also of length L0. So in their rest frames, the train and the tunnel have the same length. Bandits try to capture the train by placing doors on either side of the tunnel. The question is it possible to close both doors and trap the train inside the tunnel, considering relativity? So if we look at the problem from the reference frame of the tunnel is at rest, it has length L0, but the train is moving with a velocity v, and so it will be length contracted. Since it's length contracted, it should easily fit inside the tunnel, and the answer is yes, the train should fit in the tunnel. From the train's perspective, however, the train is at rest and the tunnel is moving towards the train. So in this case, the tunnel is length contracted, and in this case, the train won't fit in the tunnel. So the answer is no. So the question is, how can both of these perspectives be correct? So the key to this problem is simultaneity. And so we'll go through this step by step. So in the ground frame, let's assume that both doors close just as the back of the train enters the tunnel. So if this is our train, the train is moving to the right. Here's this red line here marks the left door of the tunnel. So right when the back of the train passes the left door, we're going to close both the left door and the right door in the tunnel. So again, the width of the tunnel in the tunnel's frame is going to be L0. The width or the length of the train is going to be L0 over gamma since it's length contracted. So we can think of the closing of the two doors as two space-time events, and we'll use the Lorentz equations to think about the problem. So the left door again closes at space-time coordinates 0, 0, so at position x equals 0 and at time equals 0, and the right door closes at position L0 and at time equals 0. So it'll be helpful to put in some numbers. So let's assume that the length of the tunnel in its rest frame is 1 kilometer, so 1,000 meters. We'll assume that the train is moving at half the speed of light, so beta value of 1/2, and the corresponding gamma factor is 1.15 like we've seen before. So the length contracted length of the train is going to be 1,000 meters divided by 1.15, so 870 meters. So we see there's about 130 meters left over between the length of the train and the width of the tunnel. Okay, so I think it's going to be easiest to visualize this on a space-time diagram because the math is simple but can be confusing. So we are going to start in the tunnel frame of reference, so the ground frame. So we've got the position is along the horizontal axis and time is along the vertical axis, ct. Every square here is going to be 250 meters. So if the tunnel is 1 kilometer wide, that would be 4 of these squares. 4 times 250 is 1,000 meters. Because the tunnel is at rest, the world lines corresponding to the left and to the right side of the tunnel are just going to be vertical lines. They're not moving in position. As time goes along, they just stay in the same spot. So the tunnel, as time evolves, the world lines of the tunnel just go straight up the page. As we've seen, the train is only 870 meters long, so we're going to kind of draw a little schematic train here, starting at the origin on the left side and going over to 870. So 3 squares would be 750, so 870 is in there someplace. Since the train is moving at half the speed of light, the slope of its world line in the tunnel's frame of reference is going to be 2, because remember, the slope of the world line is 1 over the beta value. So it's moving at half the speed of light, so the slope of this line is going to be 2 in a space-time diagram. So we've sketched in the train here. So the left side here corresponds to the back of the train, the right side corresponds to the front of the train. So we can kind of sketch in our little train as seen in the tunnel's perspective. So here's our train. Again, the left side is over on the left edge of the shaded green region. The right side is over on the right. So we've drawn the train at a time ct of negative 500 meters. Remember, on space-time diagrams, when you multiply time by the speed of light, the units are meters. So it's basically how far light would go in that amount of time. So, okay, so if we draw the train in at a time of ct minus 500, this is minus 250 there, minus 500, there's the train. So at this position, we can see that there's a little bit of the train hanging out of the tunnel, but most of the train is already in the tunnel at this point. So the left edge of the tunnel door is like right there. And so we'll assume that both doors to the tunnel are open, because remember, we close the tunnel doors at time t equals 0. So now if we let time evolve, so now we're at a time of ct minus 250 meters. The train is like, the left side of the train moved from here over to there. So again, time goes up the page. So it's getting farther into the tunnel. Only a little bit is now sticking out of the tunnel. Most of the train is inside the tunnel. Both doors are open. And now at time t equals 0, the train is now on the x-axis, so the ct equals 0 line. At this point, once the left edge of the train goes into the tunnel, we shut the left door of the tunnel, and we also shut the right door of the tunnel. So these are going to be our two space-time events marked L and R that we're going to be using in just a minute here. So from this time forward, the left door and the right door are both closed, and the train is completely trapped inside the tunnel with both doors closed. So we let ct evolve up to 125, that's half a square. We see that the train is roughly centered inside the train, not exactly centered, but close. Both doors are still closed. When ct is roughly 250, not precisely, but approximately 250 meters, then the front of the train gets over to the right tunnel door, at which point we're going to have to open that door to let the train out. And then at ct of 500, now part of the train is poking out to the right of the tunnel, and it's going to keep on going. So in this diagram, remember, the shaded green represents the position of the train, the brown represents the tunnel, and then our two space-time events, L and R, represent where the left tunnel door and the right tunnel door close to trap the train. I've also drawn in this kind of vertical red line, kind of showing that this left-hand door could remain closed. The right-hand door has to open up at some point to let the train out. So after roughly about 250 ct of 250 meters, then the right-hand door is going to have to open up to let the train out. All right, so let's do a couple calculations. The question is now, when does the train see the doors close to try to trap it in there? So we're now switching to the train's frame of reference. And the question is, from the O prime frame, when do we see the left door close to the tunnel? So that was, remember, our space-time event was in the tunnel frame. X comma CT was just at 0, 0. If you plug that into the Lorentz transformations, you get 0, 0 out. So this left door in both the train reference frame and the tunnel reference frame, that left door closes at time t equals 0. Okay, now the question is, when does the right door to the tunnel close? So the space-time coordinates in the tunnel frame of that right door closing we found were L0, comma 0. So we're going to use the Lorentz transformations to plug in L0 for x, 0 for t. And we get this expression that the time in the train frame is gamma v L0 over c squared. If we multiply both sides by c and then combine the v over one of those c's to make a beta, we get that ct prime equals minus gamma beta L0. Okay, so a pretty simple expression for the time at which that door closes in the train's frame of reference. Notice that this is a negative number. So beta is positive, gamma is positive, L0's positive. So since there's a negative sign here, it says that the right door actually closes before the left door closes, as seen from the train. Because remember, the left door closed at time t equals 0. So if this is negative, it's going to close before. We can find the position of the right tunnel door in the train's frame by using this Lorentz equation. We plug in, again, remember, the time that the right door closes is at 0, so plug in 0. The x position is L0, so we just get gamma L0. If we use the parameters that we picked before, 1,000 meters for the length of the tunnel, beta's 0.5 and gamma's 1.15, then these are the space-time coordinates for where that right door closes, as measured in the train's frame. Okay, so let's go back to our Minkowski diagram again. This time, though, we're going to plot the Lorentz transformations on our diagram. So the horizontal axis is still the x-axis as seen in the tunnel frame. The vertical axis is still CT as seen in the tunnel frame. But now we've overlaid some other axes to show us what the train's frame is. So this line cutting across like that is the x prime axis. So by definition, that's when CT prime is 0. This axis is the CT prime axis when x prime is 0. And I'm going to draw where our space-time events are the closure of the left door, the closure of the right door in our, tunnel frame, right here and here. To read off of our diagram what the CT value is of the right door closing as measured by the train, well, we just extend a line parallel to the x prime axis until it runs into the CT prime axis, and you can, we just calculated it, that value is going to be minus 575 meters. So if we go back to this page, we see that CT prime was minus 575, and remember the x prime is going to be 1150. So again, if you extended this line off here and read off of the CT prime axis, that's going to be minus 575. So that should look kind of right. So if you can see it, here's the tick mark for the first grid. It's like right here, so that would be minus 250 for CT, minus 500 for CT, minus 750 for CT. So it makes sense that minus 575 would be between the second and third tick marks here. We can do the same thing for the position of the right tunnel door. So we draw a line parallel to the CT prime axis up to here, and our calculations showed it was 1150. Makes sense. There's 250, 500, 750, 1000. So 1250 would be here. So again, that kind of makes sense. Okay, so I just wanted to kind of see how our calculations with the Lorentz transformations translate over to reading off things off of the Minkowski diagram. Okay, so we are going to now draw in the train on the diagram. It's exactly the same that we saw before, but in this case, it's very simple to know where to draw it. We don't have to calculate the length contraction. All you have to do is count off on the x prime axis. There's the first tick mark, 250, 500, 750. There's 1000 right there. You can draw it in. This is the exact same shape that we saw in the previous slides when we were plotting it in the tunnel frame. Okay, so here's the train. Here's the tunnel. Tunnel is particularly easy, right? Its left edge is at the origin, and then you count over 4 boxes on the x-axis. So this is exactly what we had before. I'm showing you where the doors were closed by the red lines. Okay. Now what we want to do is draw in the train in the O prime reference frame. So how does this work? So this axis right here is when CT equals 0. The grid line below it is at minus 250, minus 500, minus 750. So this line right here corresponds to CT prime of minus 1,000 meters. So let's look and see what's happening here. The left part of the train here is to the left of the tunnel. So this part of the train is sticking out of the tunnel at this time, and about half of the train is actually inside the tunnel. Okay. If we advance up to let time go forward to minus 750 meters, so we've moved up from the 4th to the 3rd box below 0. So this is at minus 750 meters. It's a little bit more of it is now inside the tunnel, a little bit less is hanging out. Now finally here, look at where the right space-time event is. This red dot is below, if you can see it, it's below this line. Remember, this was at minus 575 meters, and this line is at a CT prime of minus 500 meters. So we've now advanced time beyond the point, so the right door has closed at this point. So the right door to the tunnel will be closed. Most of the train is now inside the tunnel, but notice the left door, we haven't advanced up in time to the closure of the left door. So we see that right door closes first. Most of the train is in there, but we still have some of it sticking out the left side of the tunnel. At time CT of minus 250 meters, more and more of the train is inside. In fact, the right side of the train is very close to coming out the other side. So roughly, that's not exact, but roughly around minus 250, we have to open that right door so the train doesn't run into that right-hand door. So at this point now, we had the right door closed for a while, but now we're having to open it up before the left side of the train actually makes it into the tunnel. So we're not doing a very good job of trapping the train in the tunnel at this point, because the left part's still sticking out. We tried closing the right door, but now the edge of the train is already at that right-hand side of the tunnel, so we're having to open it up. If we advance a little bit farther to minus 125, that's a half of one of these tick marks, we see, if you look carefully, a little bit of the train is poking out of the left side of the tunnel, a little bit is poking out of the right side of the tunnel. It clearly is not fitting inside the tunnel. Both doors are open. When we get to CT prime equal to 0, that's when the left side of the train just passes the left side of the tunnel. We now can close the left side of the door. We can now close the left door to the tunnel, but now the front of the train is already poking out from the tunnel. So again, we're not trapping it in there. And if you go forward, then, we just have to keep that right-hand door open until the train leaves. So to recap, in the train frame, the tunnel doors are never simultaneously closed, and the train is never completely inside the tunnel. In the tunnel frame, the tunnel doors are simultaneously closed while the train is inside. And this is an illustration of the relativity of simultaneity. Things that appear simultaneous in one reference frame, such as closing the doors to the tunnel, aren't simultaneous in a different reference frame. That is the reference frame of the train itself. So what do we make of this? How is it possible? How is it possible for both of these perspectives to be correct? Well, it's possible only if we give up this notion of simultaneity as being an absolute thing. People measure time differently, and the closing of the left and the right doors depends on how we're measuring time from the moving reference frame versus the reference frame that's attached to the tunnel. So both perspectives are correct. One observer sees the train completely inside the tunnel with both doors shut. The other person doesn't. That's one of the implications of special relativity, that we have to give up our common sense notion of how space and time work. All right, so you'll explore this problem a little bit more in one of your homework problems.